Good afternoon everyone. My name is Rupa Rani and I am teaching in Akgec in CSC department. Today I will teach you red black tree. First of all, why we need arbitrary red black tree? Actually there are some limitation in binary search tree. That's why we are studying red black tree. Now we will see what are the limitations in BST or binary search tree. You may see here, this is a tree and there are 7 elements in this tree. You can see the question, draw the BST of height 2, 3, 4, 5, 6 for the element these. These are 7 elements total and this is the tree of height 2. Here height 3 and 3 is like this. You already know how we draw the binary search tree. Now see the next one. This is of height 4. From here you can calculate 1, 2, 3 and 4 for the same elements. Now see the next. This is height 5. 1, 2, 3, 4 and 5 for same elements. And next is the height 6 and there are 7 elements in this. 1, 2, 3, 4, 5, 6. Total elements 1, 2, 3, 4, 5, 6, 7. Means maximum height is 6 in this binary search tree for 7 elements. See here, minimum height is 2 as you saw in the first tree and maximum height is 6 like this. Means if we find out the time complexity for best case and worst case, then how we will find minimum height? When minimum height is 2, then time complexity is log n. How it is log n? Because we already know that elements are 7 and log 7 base 2 is equal to 2.81 approximate value. Means this is near about 2 and height is also 2. It means we can write it log 7 base 2 and 7 is number of elements which we denote by n, by using n. So we can write it big O log n base 2. Now next is maximum height 6. This is worst case because here maximum height is 6 and if I say total elements are 7 and it is 6, means 7 minus 1 6 and 7 is equal to n. These are number of elements. It means time complexity is big O n due to this n minus 1 because this is the constant and we ignore the constant value when we find the time complexity. So this is big O n. In this way we can say for a binary search tree maximum height for 7 elements is 6. It means this is n minus 1 or we can say time complexity is big O n. When we take the minimum height it is 2 and when we are finding height 2, when log 7 we are taking total number of elements 7, then when you find the value of log 7 base 2 it is approximately 2.81 which is equal to this 2. It means time complexity is this log 7 base 2. 7 means n. So we can write it log n base 2. This is log n base 2. Correct? This is the time complexity. Means in worst case time complexity is big O n, which is a limitation. While when we study the red black tree, time complexity will be log n in all the cases, worst case, best case and average case. Means we will overcome the limitation of this binary search tree, which is in the worst case, this one in the red black tree. Now see the next slide. Overall, we can conclude in red black tree maximum height in best or average case is log n, so that all operations take bigger log n time on average. Now we will start with the red black tree. First, what I saw that the limitation of BST, where time complexity is big O n in worst case, we are overcoming that limitation in this red black tree. Now start with the red black tree. Here AVL trees are self balanced tree. Red black tree is also a balanced tree, and the time complexity is big O like log n in average and worst case. Then why we need arbitrary? Arbitrary and AVL tree are approximately same. That's why I am talking about this arbitrary. Before understanding the arbitrary, we will understand that why we need arbitrary. While in AVL tree, these are self-balanced tree and same time complexity. In AVL tree, actually, sometimes we need to do many rotation to balance the tree. If tree become unbalanced after doing insertion or deletion operations, but in arbitrary, it guarantees that at most 2 rotation would be required to balance the tree. Means we are using only 2 rotation to balance the tree in arbitrary, while in AVL tree we can have many rotation to balance the tree. So this is the difference between AVL tree and red black tree. Next, sometimes rotations are not required. Only recoloring is sufficient to make the tree balanced. In AVL tree, these are strictly height balanced tree, while arbitrary are roughly height balanced tree. But arbitrary guarantees that time complexity will be big O log n for all the operations, either insertion, deletion or searching, while this doesn't occur in AVL tree. So this is the difference between AVL and red black tree. Now this is the introduction of red black tree. We start with this. Actually a red black tree contain 5 field. Here I have written 4 field, but actually it contains 5 field because I didn't include this color, which is red or black. What are those 5 field? First one is key value, left child pointer, right child pointer, and a color field. If we draw it in a box, first one is color, left value, right value, key value and parent value. This is right, this is parent. This is left pointer, key value, what we are taking. This is the parent, and this is right, and this one is color. Actually these are 5 field, but in general we say these are 4 fields, right? Now apart from other restriction of binary search tree, the red black tree has the following properties, following 5 properties as you can see in the PPT. First one is color of node is either red or black. In any arbitrary, node is either red or black. Second, root node is always black. Third, all leaf nodes are black and no data is stored in the leaf node. Fourth, every red node has 2 child. Every red node has 2 child. They both must be black color. Next is fifth, every simple path from a given node to any of its leaf node has an equal number of black node. I will show you these 5 properties in a diagram. See this diagram. In this arbitrary. First property, every node is either red or black. Black color is denoted by this black and red color is denoted by this blank rectangle box. In this tree you can see every node is either red or black. Root node is always black and every red color node has always two children and it is either black or it is either red. This is the fourth property. Every red node has both children colored in the black or no two adjacent red nodes are allowed on the same path. Means every red node has always two children. Like this. This node has two children which are in black color. And every leaf node is always of black color. All leaf nodes, these null nodes are the leaf nodes are in black color. And the last property, height will be same of every leaf node from any node. Like we are calculating the height of this node, black node height. The black node height of this node is 1 because here only 1. And if we see this one from this node, then also here is 1 because black node is only 1. Again we will see the height of this node. Black node height of this node is 2, 1, 2. If we check this from here, black node height is 1 and 2, same. Means all black node height from its leaf node are these. It must be same for this node. If we check for this one, then black node height is 2. From here, this one black node and this one black node, so 1, 2. If we check from here, then 1 and 2, same. Suppose we check from here, we can see from this 1 black node and 2 black node. So height are same from every leaf node. So these are the 5 properties of red black tree. Suppose if any tree, any red black tree, this root node is red node, then by default we will color it in black because of the property of red black tree. You can see here in the first diagram, in A diagram, the root node is black color, 16 is of black color, sorry, red color. This is of red color. So by default we will color it black because of the property of red black tree. Every root node is always black. So these are the properties. Now there are various operations in red black tree. First one searching, second insertion, and third is deletion. We will see one by one all the operations. First one is performing a read only operation on a red black tree requires no modification from those used for the binary search tree. However, in insertion and deletion operations, it may violate the properties of red black tree. Means we will see, basically we will understand the insertion operation and deletion operations. Now start with the insertion operations. The insertion operations start in the same way as we add a new node in the binary search tree. In a binary search tree, we always add the new node as a leaf node, while in a red black tree, leaf node contain no data. As I told you in the property of arbitrary, leaf node always will be in a black color. Instead of adding the new node as a leaf node in arbitrary, we will add the new node as a red interior node that has two black leaf nodes. Like suppose we have a tree, values 2, 1, 5, or sorry, this is 4, this is 3. See another 4, 3, and this one is 5. And this is of black color, this is black color, and black. This is of red color. Double circle is red color. Then new node is, suppose I have to add the new node. That new node is 2. When I add the new node, it will always in red color. By this line we understand that new node, when we add the new node in red black tree, it must be in the red color always. Either it violate the property or doesn't violate the property. If it violate the property, then we will understand the different cases to resolve this issue. I think this is very much clear to you all. Now, there are the several cases to perform insertion operations. We will understand these operations one by one in the next lecture. I conclude the last few points what I told you in this lecture. First one, I told you what are the limitations of binary search tree. Binary search tree limitations is time complexity, that is big O n in worst case. To overcome that limitation, we are studying arbitrary, where time complexity will be big O log n in all the cases. Next, we understood that what is the difference between AVL tree and arbitrary. Basically, there is only one difference, that there may be several rotation in AVL tree, while in arbitrary there will be only 2 rotations to balance the tree. Both are balanced search tree. Next, we understood the what is the red black tree and what are the various properties of red black tree. 5 properties we understood in this lectures. That's it. We will understand these cases in the next lecture with the example. Thank you everyone.